a variation on this, or sort of a combination, right? When we do a Michael reaction, and then in our product, if we can do an intramolecular aldol reaction, that will form a ring with a lot of useful things attached to it. It's referred to as the Robinson annulation. Annulation comes from a word meaning ring forming. So let's just go through the mechanism of this. We have 3-butene 2-one, so it's an enone. We have ethyl acidoacetate. So this is going to do a classic Michael reaction. With sodium ethoxide here, we will deprotonate the stabilized alpha position of ethyl acidoacetate. Our Michael reaction will occur, giving us the this intermediate. Right, here's CO2ET. Like that, right? We end up with an enolate on the alpha hydrogen, but then just the solvent can protonate that. Right? Every time we use ethoxide to deprotonate, we make one equivalent of ethanol, which I can use to reprotonate. Okay? So there's our Michael product, but then if we look carefully, I have a carbonyl that is 1, 2, 3, 4, 5, 6 from an alpha carbon. What I can do with another equivalent of ethoxide is make the enolate right here from the carbon on the end. And what happens, it'll do an aldol reaction. Remember, that's just an enolate adding to a regular ketone. That'll give us a 6-membered ring. O2ET, where right here is the new carbon-carbon bond that we've formed. We'll have a couple things here on that carbon. We'll have an alkoxide. We'll have the methyl that was there originally. Okay, so the solvent will protonate that alkoxide. We'll end up with a regular aldol product. Oops, OH. Which then can be dehydrated like aldol products tend to do to form this enone ring, right? It's alpha beta unsaturated within the ring. So if our product has a 6-membered ring, which is an enone, okay, so a carbonyl and it's alpha beta unsaturated within the ring, that's very commonly made with the Robinson annulation reaction. So let's see if we can figure this out. Here's a complicated product. Okay? It's got 2 fused 6-membered rings, but it has an enone. Okay? And if we look at our reaction up above, the carbon-carbon bond that did the ring forming was the bond that eventually became the alpha-beta double bond there. So when we're doing retrosynthesis here, it's that alpha-beta double bond that was the last thing to be formed. So breaking that bond, methyl groups, it's a carbonyl. This right here was our original alpha carbon, and that added to a carbonyl. Okay, so that's just the classic aldol disconnection, where we disconnect the double bond of the enone, right, where one carbon was the enolate, on the other was a carbonyl that was added to. Then, if we look at this product here, this is a beta diketone, which we could have done a Michael reaction to. So here is the alpha carbon of that, which was negative. And remember, a Michael reaction adds to the beta carbon of an enone. So the compounds we would have ended up with was this cyclohexane dione. Here it had a methyl group. The middle carbon had geminal dimethyls on the other side. Our enone looked like this. Alpha, beta being unsaturated. So those were our reactants. Let me take you through this reaction here. We have our beta dicarbonyl. Methyl in the middle, gem dimethyl. We will deprotonate. The base for this one can be whatever we want. There's no esters involved. We could just use hydroxide if we wanted. Whenever there's an ester involved, your base has to match that ester, remember? But here we have just a beta diketone, which can be deprotonated with plain old hydroxide. Okay, we add that to our enone. Remember what happens there. We get addition to the beta carbon of the enone. It makes a C- on that alpha, but that just gets protonated again. So what we have is this compound, alpha, beta, there's the new bond. Okay, that's the Michael product. All right, look at this. This is a 1, 2, 3, 4, 5. It's a 1,5 diketone, just like any Michael product should be. But it is also able to undergo aldol reaction because this carbonyl right here is 1, 2, 3, 4, 5, 6 from another alpha hydrogen. So additional base can form a probably small amount, but you don't need much to form because the ultimate product is so favorable. Form the enolate right there, alpha to this carbonyl way out there. So that undergoes aldol reaction. Let's add our reaction names. This was Michael up here. Our aldol product, anyway, after we protonate the alkoxide, looks like that, which can be dehydrated to form our final product. There, which is an enone. Oh, got the methyl group there. Having a complex product like this, you break it down one step at a time. Okay? The very last thing that happens is formation of this enone. So if we can imagine disconnection there, then before that we can imagine that a Michael reaction can happen, right? Because this could make a stabilized enolate. This could add to the beta carbon of that enone right there.